Hello from my side. My name is Panagiotis Aivaliotis and I am a research engineer and BPT candidate at Laboratory for Manufacturing System and Automation in the University of Patras. I will present you the paper entitled Machine Behavior Prediction Tool for Maintenance Applications. This work is a part of programs project which focus on predictive maintenance. The main objective of the paper is to present a model-driven approach for prediction. Starting from the challenge definition, today there are lots of traditional maintenance strategies with no specific knowledge of machine health status, no prioritization of maintenance activities, and with lots of breakdowns of the production plant for maintenance reasons. Program's vision is to create a framework for more accurate identification of the maintenance tasks, the prioritization of maintenance tasks based on prognostics and failure analysis, and the developing utilization of physics-based virtual models and digital twin concept for the prediction of machine health status. One demonstrator of programs project comes from solar industry. More specifically, here you can see an image from the production plant which produces solar boilers. Programs uses a number of sensors and machines controllers in order to collect all the required data through the ECN, the equipment control module, and then all the data are provided to the different module of programs for failure analysis, calculation, etc. The proposed approach for the remaining useful life calculation consists of the data gathering of machines through the machine controller, through the external sensors like proximity sensors, vision sensors, as well as data coming from the machine's manufacturer, like reliability parameters. In programs, we also use physics-based simulation models for the monitor of unreached data through virtual sensors. Moreover, physics-based simulation models are used also for the prediction of the future degradation of the machine. All these modules and data are used for the rule calculation. Initially, in programs, we created an advanced physics-based modeling methodology for a machine. This methodology consists of three main phases. The first phase is about the modeling of the dynamic behavior of the machine. The second one is about the modeling of the virtual sensory side, the digital model, and the third one is about the definition of the modeling parameters of the model. Each phase will be analyzed below. So, starting from the first phase, we talk about the modeling of the dynamic behavior of the machine based on the kinematic model of the machine and the structural model of the machine. Each element can be modeled as a black box, gray box, or white box. In the right side of the slide, you can see an indicative example how this model is. Here you can see the implementation of this first phase in programs project. More specifically, we have created a digital model of a robotic structure. This model consists of a number of components like the actuator, the gearbox, and the mechanical structure, while each of these components consists of some components. For example, in mechanical structure, you can see here that there are some components which represent the real machine's joints and links. The physics phenomena are embedded inside these subcomponents. In the second phase, we talk about the modeling of virtual sensor aiming to collect data which we cannot gather using external sensors. In the right side of the slide, you can also see an indicative example, while in the next slide here you can see how we use the we have integrated the virtual sensor inside the digital model, and more specifically in the gearbox component of the digital robotic structure. More specifically, here you can see three types of virtual sensor. We have one virtual sensor to monitor position signals, one for velocity signals, and one for acceleration signals. All these data are used for the rule calculation. Then we have the third phase, which is about the definition of the modeling parameters. As modeling parameters, it mentioned to the parameters which should be tuned, which should be updated over the time, aiming to enable the digital twin concept. In programs, we have created a MATLAB code which identify the values of these parameters based on the real data coming from the machine and the external sensors, and then the identified values of the parameters are imported in the digital model. Regarding the tuning of the of the models aiming to enable the digital twin concept, we can say that the steps are, first of all, the data gathering from the real machine, then the analysis of them, and data synthesis techniques are performed, aiming to identify the values of the modeling parameters. These values are imported inside the digital model, aiming to have a digital representation of the real machine, which will have the same behavior as the real one. Talking about digital twin, I would like shortly to highlight that as digital twin, we talk about that if we provide the same input to the real machine and the digital model, then the real output of the machine and the simulated output of the digital model should be almost the same. Regarding now the rule calculation, as I said before, we use data coming from the real machine controller, from sensor and virtual sensor. Of course, inside the virtual sensors and the digital model, we're taking also under consideration the future production plan. So we have we collect data from the ERP system of the production plant. For the data acquisition, we use some technologies like Fiber IoT and Open IoT frameworks. And of course, we perform data synthesis and analytics aiming to calculate the remaining useful life of machine's components. Then, based on this remaining useful life, we go ahead with the prioritization of the maintenance tasks, taking, of course, under consideration the production plan of the industry. Here, you can see an indicative example from the rule calculation. First of all, in all these figures depict the torque signals of, and for more specifically, the orange one is the nominal torque signal, while the blue one is the predicted torque signal. So we have make simulation for 1 month of a virtual operation of the machine, 3 months virtual operation of the machine, and then 6 months virtual operation of the machine. As you can see, in the 1 month virtual operation, the nominal torque signal and the predicted one are very close. Similarly, in the 3 months, but in the simulation after 6 months of virtual operation, you can see that there is a big deviation between the orange and the blue signals. We talk about the right diagram. Then we can calculate the rule based on the maximum allowed deviation, which is defined by the production manager of the production plant. More specifically, here you can see that in month 6, the deviation between the two signals, the two torque signals, are bigger than the maximum allowed. So we can say that the remaining useful life for the axis 1 of the robot is 6 months. Of course, this is an indicative example, and in programs we calculate the remaining useful life in a daily base. As conclusion, we can say that the aim of the present approach is to provide a satisfactory solution for the calculation of each machine's component rule, aiming to be used for predictive maintenance. The direct benefits are the online prediction of the machine health status without stop real machine's operation using simulation models. The gathered and predicted data can be used as input to statistical analysis for the prediction of the machine health status, and the user is able to know the future machine's condition and how it will be affected by the execution of a task even before its execution. So, all these activities have already performed in programs, and now we are working with the final integration of the module in our demonstrator. As I said before, all these activities took place in programs project, prognostics-based reliability analysis for maintenance scheduling, which is the full title of programs, has received funding from the European Union Horizon 2020 Research Innovation Program. Thank you very much.